Good morning, everyone. I'm Jijun Tan from Shenzhen University of Advanced Technology, which is a new university in Shenzhen, which is a research university. Today, my topic is bridging the biophysical gap, holistic environmental awareness for 3D linker design. This is a work by and the chemical and physical design for drugs. As you can see from the title, our core objective is to bridge the gap between purely geometric generation and the complex biophysical reality of protein environments. So in the field of structure-based drug discovery, we need to connect molecular fragments to design functional linkers, which remains a significant bottleneck. The new framework, which is called LinkerBridge, is designed to move beyond simple geometric completion towards holistic environmental awareness, which need to consider all the impact of both geometry and physical and chemical information. So our motivation, from the basics, why do we care about molecular linker design? So if we have fragment A and fragment B, they are very small and they are weak binding fragments that we need to bind these two adjacent pockets on a target protein, but individually, these fragments they do not have the potency to become drugs. So we need a molecular linker which acts as a bridge. By covalently linking these fragments, we can transform these low affinity hits into high affinity drug-like candidates. Essentially, linker design is the critical step that translates fragment screening success into viable lead compounds. But these compounds often struck with complexity, which we will see from the next few slides. So there are a lot of methods recently developed, but this method they often only see fragments and ignore protein environment and also ignore biochemical interactions. So this method, these existing generative methods are environmentally blind. This method also takes the two fragments as input and attempt to fill the space, but they treat the protein pocket as a vacuum. So this is a fundamentally flawed assumption. They frequently generate molecules with severe steric clashes that the atomic clash each other overlaps with the protein. They also produce structures with poor binding affinity because they ignore biochemical interactions. So ultimately, this leads to physically invalid molecules that are useless for drug design. Uh, so from our point of view, ignoring the environment is not just a minor oversight, it's a critical failure. So why is linker design so hard? So we identify three major challenges. The first is biochemical awareness. They must understand non-covalent interactions such as hydrogen bonds, hydrophobic effects, and electrostatic forces. Uh, the second challenge is the spatial constraints. Uh, so because we know that protein folding is they are incredibly crowded. So it's not building something in the open space. So designing in such crowded protein pocket is more like navigating a minefield of atoms. Third, we need to joint optimize all these constraints. They must satisfy simultaneously, such as geometry. We need a correct 3D conformation and spatial arrangement. And also we need plausible bound types, which are stable and easy to be synthesizable. And also they need to have a biology function, we need favorable interactions and high binding affinity. So let's summarize. Link design is difficult, requires integrating biochemical interactions, spatial constraints, and multi-objective optimization. Uh, Simultaneously, to optimization. So the overview of the method, which is we need to have 5 steps. So we need to have the interaction awareness representation of the atoms. So we encode the biochemical context of the pocket uh, using an interaction map. So we have the interaction map, which is a vector for each atom that if they have interaction with one or two other atoms, so we can this vector is 4-digit vectors. Then the second step, we have the physical guidance. We introduce multi-scale physical fields to guide the generation process, which will be away from steric clashes, which of the so the atoms they do not overlap with the protein. We use as other methods also have done. We use diffusion generation, which we utilize a structure-aware diffusion model, which is conditioned on the features and guidance from the previous steps. The last step, we obtain high-quality linkers that are both chemical reasonable and biologically compatible. Uh, so summarize, the LinkerBridge essentially teaches AI to see the environment and can feel the physics. There are a few innovations. So the first one is the interaction-aware representation. Existing diffusion model only see geometries, which each atom has the coordinates, and we know the atom types, and also we know the distance. But it missing they miss biochemical context, such as hydrogen bonds, hydrophobic patterns, electrostatic preference, and pi-pi interaction, which are the electron interactions of the cloud. So we extract specific interaction features such as potential hydrogen bonds and hydrophobic contacts, and inject them into the latent space of the diffusion model. This is very crucial because molecular coordination is governed by these non-covalent interactions. So by encoding this information, we not only consider merely the geometry-aware generation, but we consider more realistic biochemically aware generation. So we teach the model what the protein pocket actually prefers, not just what it fits. So basically, we move from geometry-aware generation to biochemically aware generation. The key insight is learning how the protein environment interacts with molecular fragments before generating the linker, which will make the model more realistic. And before it makes mistake, we actually use more constraints from the biochemical information. The second innovation is using the uh, physical aware diffusion guidance. So take the issue of physically feasibility through physics aware diffusion guidance. So as we can see that standard diffusion models optimize from likelihood, not physics. So this often results in atomic overlaps and unrealistic structures during the denoising process. Uh, to fix this problem, we introduce a differentiable van der Waals energy, which we use it directly into the denoising loop. So here is the formula of the loss function. We used van der Waals ready RIRJ and the interaction distance Dij. We calculated the energy penalty, but we then compute a gradient from this energy and use it to navigate the denoising trajectory away from high energy collection states. So this is instead of random denoising, the method follows a physically grounded path, ensuring the generated structures are theoretically allowed. So to summarize all these group steps, so basically we have the extractions, and then we generated the interaction aware using the embedding is simple as we said before, and we add fusion the features and we use equivariant message for the confirmation. So we make sure they are not dependent on the coordinated system. And also we use the diffusion physical guided diffusion because we use the van der Waals guidance of the gradient, and then we generated the 3D linker. So why do we use the EGNN, which is using the E3 equivalent based on the Euclid coordinate system? So because we want the model to be invariant of translation, rotation, and it has the reflections as well. So we generated the molecules that are both chemically meaningful and physically feasible from this method. We designed the experiment to evaluate our method with other methods. So the left are the data sets are often used in the literature, which is the first one is uh, the ZINC and CASIF. They are for the standard linking. GEOM is for multi-fragment linking, and BindingMOAD for protein conditioned design. So we trained over 900,000, about 1 million samples. So we used 4 benchmarks and covering 3 design scenarios. So crucially, this method they called LinkerBridge isn't just a one-trick method. So it handles dual fragment linking, multi-fragment assembly, and target conditioned generation within a unified framework. So this allows us to rigorously test the model against increasingly complex challenges, which makes us closer to the real-world drug design, drug discovery scenarios. So we can see from the result there are this kind of metrics are widely used by the other literature. So the first one is the QED, which is the quantitative estimation of a drug alike. So basically, it's a measurement of if this molecular looks like a drug. So we compared with other methods, the one or the three, four other methods. From the QED measurement, we are much better than the other four state-of-art methods in the ZINC and CASIF dataset. The SA quality is the measurement of how easy they can be synthesized, to be created. In this measurement, the larger the better. So our method is also better than the other method. The SC RD kit is a confirmation calculate the score. So if the structure looks good or not. Our method is also better than the other method. So we got the state-of-the-art performance on both ZINC and CASIF benchmarks. So we also do the multiple fragment linking. So we use on the GEOM dataset. So we have multiple 3 fragments. We connect these 3 fragments with a single shot linking, so simultaneously. So we cover 87% of the linker and achieve SC RDKit score of 0.93. So it's very important because traditional methods they generally handles only 2, so they struggle with complex multi-fragment systems. And our method can generate all connections simultaneously in a single generation process. So that's very important in the real-world design. So we also compare with other methods to see why physical guidance matters the most. We did the steric clash analysis, which is to see if atoms overlap with protein or not. We have so using the diff linker is the other method. They have a very high collision frequency and with very more steric violations. And using LinkerBridge, we can see that the clashes are reduced because we have physically realistic structures which are closer to the ground truth. So our conclusion here is that the physical guidance effectively prevents unrealistic molecular conformations. So makes it more realistic. So we did ablation test. So if we remove the interaction module, the QED dropped, and because it's a loss of biochemical awareness. If we remove the one-to-one guidance, the method gets more steric clashes. So from this ablation test, we know that it's important to integrate both interaction awareness and physical guidance to get the best performance. We did it on some of the test, the structures. So we the LinkerBridge successfully reconstructed a known inhibitor. So crucially, it preserved key hydrophobic interactions within the pocket. So if we evaluate the docking performance, the generated linker outperformed the referenced compounds. So it shows that LinkerBridge does not just generate pretty structures. It actually generates molecules with improved binding potentials. So we also have the case study for the scaffold hopping, that which we can change the structure to see if we can achieve better potency of the drug. So the second case study demonstrated scaffold hopping, so which we can explore new novel chemical space. So it didn't just recover known scaffolds. It generated novel ones while preserving the biological activities and improve the target selectivity. So the key finding here that it not only recover the new known scaffolds, but it also can generate novel scaffolds. So LinkerBridge supports both scaffold hopping which can maintaining functional binding patterns. So to summarize, our innovation is basically we not only use interaction of our representations, we also use physicals of our diffusion guidance, and it achieves better performance, not only better chemical quality, better structure, and it achieves fewer clashes, and also it has better pocket compatibilities. So this method it's an end-to-end method, so it's very practical in the drug design. So we not only can link fragments, two fragments or multiple fragments, we can get new structures from the existing scaffold, so which enables us to do structure-based drug design. So this is our conclusion. And for the future, we need to integrate more, richer protein context. We can get some other method that use enforcement learning. We can learn from that to do more target protein degradations, and we can try to, if we can make it realistic to be utilized in the drug design of the optimizations, and we can also try to unify generative models across drug discovery tasks. So to summarize, this method paves the way toward intelligent, context-aware, and physically grounded molecular design, which we hope can be used for the next generation of drug design. And that's all for my today's presentation. Thank you.